A2 further maths, transformations of curves. Okay, so what we're going to do is just a bit of a recap of your first year skills. So transformations of some of your conic sections that we did in the first year. If I'm asking you to translate by AB, how would that look on the function? What would you do? Okay, so hopefully you've either guessed or you've calculated that you can work out a translation of AB by replacing the x for x minus a and replacing the y with y minus b. So you could probably guess it that way round, but it's making sure that you can also see it this way round as well. If you replace the x with x minus a, it's a translation. So how does that look? So if I've got this one here and I want to translate it by a certain amount, a certain amount A and a certain amount B, what happens is it moves it across and up by that vector AB. And there we go. That key point just there would mark up and across to just there. Okay. Right, we also looked at last year, what happens if you had a stretch in the x-axis by scale factor A? What would you do there? So again, pause if you want to, have a think about it. Right, so we'd replace x with x over a. Remember, it's the opposite way around. So replacing x by x over a, and that would be a stretch by scale factor a. What about the y? Same idea. Y will be replaced with y over b. Just be very careful. It's very easy to sort of get used to seeing the sort of things you hear in your normal maths, which is that x does the opposite and y does the same. And the reason why it's different, or it seems different for these conic sections, is because the ones you look at in your normal maths are usually y equals equations. Okay, so these aren't, these are ones that are more like x squared plus y squared equals 4, like a circle equation. All right, it's very different then. Okay, so what does that do? Take out circle, like I just mentioned, x squared plus y squared equals 12. And if I stretch that in two directions, then it becomes an ellipse. And there we go, that the x value is replaced with x over a, and that stretches the whole thing out. It's been pulled out by scale factor a in the x direction. The y has remained the same. What about an enlargement by scale factor a? So that's similar to a stretch, except an enlargement means that you're enlarging both the x and the y by the same scale factor. So the only difference in that is that you replace the x and the y by that same scale factor. Okay, right. So I've got that one just there, x squared, y squared minus x squared equals 1. And if I'm going to enlarge that by a set value, so in this case, enlarge it by scale factor a, it means that both the x value and the y value are over a. So there we go. You can see how it's just been stretched out and made that bit bigger. What's important though is the fact that these two are the same value, so it's divided by the same amount. Okay, what about reflection? So reflection in the x-axis. See if you remember what that one is. So we want to think about is the x squared. How can x squared go from there down to here? Then you're replacing the y value for minus y. Okay, so you're putting a minus on the front of the x, or you can put a minus sign in front of the y. But it's good practice to get used to doing it for the y value in this case. And the same with the x-axis. It's like replacing the x with minus x. So I'll give you an example. If I want to reflect that graph just there in the y-axis, what would I do? I would take the x value and I would change that to minus x. So therefore I get that equation, or y squared equals minus 2x when I expand it. Okay, so reflection of the line y equals x. So what happens if I reflect on the line y equals x? So I'm sure you could tell me. Then we replace the y with the x's and the x's with the y's. So we literally just swap those two over. Very similar to how we find the inverse of a function, because an inverse is a reflection of the line y equals x. A reflection of the line y equals minus x. I replace the y with minus x and the x with minus y. So remembering to replace both of them with their negative values. So for example, in this case, x squared plus 8y squared, so that ellipse there equals 16. If I'm reflecting that in the line y equals minus x, so I'm reflecting it down here, then what do I get? I get minus y squared just there, okay, which goes plus y squared, but it definitely goes to those two parts. It's gone from there to there, it's been reflected downwards, and the x value is also reflected. That's why that one there has gone from there, and if you reflect it, it will go down to here, just to there. It's been reflected like that. Okay, so have a think about this, try doing it yourself. A straight line 2y minus x equals 1 is rotated 90 degrees clockwise about the origin. What I'd like you to do is think about what's the equation of the new graph after you've done that transformation. So have a go yourselves, think about sketching it, think about rotating it 90 degrees clockwise and see what new graph you do. So pause there, have a go at that yourself. Okay, so let's see what you got. So there's your equation of 2y minus x. So hopefully you sketched that okay. And you're taking that graph and you're rotating it 90 degrees about the origin. So it's like sticking a pin in there and spinning this whole piece of paper around and seeing what new equation you get. So if I did that, if I stuck a pin in and rotated it, what I'm going to end up with is a line that comes down like that. You can see I've just rotated that round 90 degrees. The question is now is what's the equation of that new graph? And the equation of that new graph is 2x plus y equals 1. Okay, you can see where it crosses. It crosses when you can, so if you didn't get that, you could certainly do it as find out the gradient. So I can see the gradient there is 2 across 4 down or 1 across 2 down. So I can see I've got a gradient of a half there going downwards. Oh, sorry, gradient of minus 2. I can also see that it crosses at positive 1 just there, which is why if you rearranged it, that's where you get that value from, minus 2x plus 1. Okay, but how do we get from there to there? So you might have already started looking and thinking, yeah, I can see what's happening there. It looks like the x's and the y's are swapped over, but it's got a negative value there and a positive value there. So can I do something with that? So you can see that sort of thing has happened. The 3 has changed to 2. So the x value has changed to the y value, and the y value has changed to the minus x value. So the x value has changed to the minus y. That's what it's done there. And the y value has changed to the x. Okay, so that x value of 3 has gone to the y, but it's been negative, and the y value becomes the x value. Okay, so grab your notebooks. Transformation of curves, this is the one you haven't got. All the other ones that you had from last year, all the stretches and the enlargements, all those types of things. But these are the ones that are different. So rotation 90 degrees clockwise about the origin. A rotation 270 anti-clockwise about the origin. So what's special about those two? Yes, well spotted, they're the same. Okay, so either of those were given to you. What does that mean? You replace the x for minus y and the y for x. Okay, you need to try to remember it, try to think about what we just did, where we looked at a simple example. You could do the same sort of thing as that. Okay, a rotation 90 degrees anti-clockwise. So what happens if I went backwards? So rotation 90 degrees anti-clockwise, or of course a rotation 270 clockwise, whichever way around you say it. And what you do for that is very, very similar. The x becomes the y and the y becomes the minus x. Okay. And the way to think about it, if you just think, I've got my straightforward axes, what happens to that x value? It goes round at 90 degrees anti-clockwise, becomes the y, and what happens to the y value? It goes around 90 degrees and becomes minus x. Okay, rotation 100 degrees, 180 degrees about the origin. So if I rotated 180 degrees, what would happen to that x value? It would go round to minus x. And what happens with the y value? 180 degrees, it would go round to minus y. So well thought about if you didn't notice. The x becomes the minus x and the y becomes minus y. And it doesn't matter about the order, of course, that one anti-clockwise or clockwise, because 180 works in both directions. Okay, so what I'd like you to do is practice some of those skills. If you go to 3B on page 52, there's some extra work where you're looking at practicing some of those rotations and seeing how it affects the equations of the curves. Okay, so once you've already got that exercise, you can come back and carry on with the lesson. Okay, so let's just extend some of your knowledge then from what you did last year. You've practiced lots of single transformations. You just practiced that new transformations of rotation. Now what we're going to look at now is applying multiple transformations or composite transformations. So the example I'm going to ask you to have a look at is this situation where we have this curve, this ellipse we've got here of x squared plus 4y squared equals 16. I'm asking you to transform by these two transformations just here, and I would like you to think about the different equations you could have of your final answer, doing those in either order. So different possible transformations after those transformations in either order you like. All right, so pause there, have a think about it, think what those transformations do to the equation, and then think about applying them in any order you like. Okay. Right, so let's say if you got it right then. So the first thing you should have done is thought about how to write a translation by the vector 3, 2. So if I wanted to do a translation by the vector 3, 2, I know that means replace the x for x minus 3 and the y for y minus 2. A rotation 270 anti-clockwise about the origins. So let's think about this. There's my x-axis, okay? So if I'm just thinking about it, I could do this in my head. There's my axes. There's my x value. I rotate 270 degrees anti-clockwise. It will go to there, which is minus the y value. So definitely minus y. What happens to the y value? 270 degrees anti-clockwise. We'll take it around to there. So that y value becomes an x value. So there we go. X becomes minus y and y becomes x. Right, why does that help me? Because now I can have a go at both transformations in either order. So starting with the translation, I translate it by 3, 2. So that's taking it 3 across, 2 up, and the equation becomes that equation just there. Once I've done that, I'm then going to do the rotation. And if I do the rotation, I can see that my x value, I replace it for minus y, and my y value, I replace it by x. And there you go, there's my new equation. And you'll notice that minus y minus 3 squared could be just written as y plus 3 squared. It would have been the same thing. Okay. Right, let's look at what difference or any difference if I'd done the rotation first then. So if I do the same sort of thing and I rotate it round, what do I end up with the rotation first? Well, I end up replacing my x for minus y and my y for x, and I rotate it like that. If I now take that equation and I translate it by 3, 2, what I end up with is an equation up here. Very different to last time. Last time it was over here somewhere. So you can see it makes a difference which way round you do your transformations. Obviously, you could just neaten it up slightly. See the squared, you've got y minus 3, x minus 2 all squared, and so you end up with that equation at the end. So very well done if you managed to get that. And you can see quite clearly that the order matters. All right, you've got very different equations, or when I say very, they're not hugely different, but they are different. So it's important to make sure that you get your order correct. Right, so let's look at a slightly different one. A hyperbola has an equation x squared over 3 minus y squared equals 1. I would like to think about what sequence transformations that maps that hyperbola onto this hyperbola that looks nothing like it. Okay, so grab that down in your notebooks and give you a bit of time to think about how you could do it yourself before we look over. So pause there until you've got your notes down, you're ready. Okay, so nice and clear for your notebooks then. I need to rearrange that equation. So this equation is just given me, and it needs to look similar to this form. So in other words, it's got to be some function squared, take away some function squared equal to 1. So some function squared over 3, sorry, minus some function squared equals 1. That's how I've got to rearrange this. So how am I going to do that? Well, maybe the first thing I want to do is consider just expanding those brackets out, and then I can start to put the some function of y's together, some function of x's together, so the x's together and the y's together. So I've got that. I also need to have a 1 on the side, so maybe just adding 1 to both sides or something like that, or adding 3 to both sides, sorry, we'll sort that out to be 1. That could be an option that I have in my head. But let's see what works best. So I'm putting all the x's and y's on one side, the 2 on the other side, and that's why I've got positive 2 now, which is quite good because I wanted 1, so it's almost there. I've got my y values. There you go. So I've got some function of y squared. I've got the x value just here. So if I think about the x value, I want some function of x squared over 3. Now I could get this over 3 quite easily. I could just put a line and say 3 underneath. But to do that, I'd also have to times the top by 3 as well. So I can definitely sort out this part and write this as 6x squared over 3. And that would be the common mistake people do. Because don't forget, this function here has got to be squared. So it would be root 6 all squared over 3. But let's go do one bit at a time. So I'm adding 1 to, I'm sorry, I'm taking away 1 from both sides. I'm doing that because now I've definitely ticked off this part. I'm stuck with this minus 1. I might put that with the x squareds. I might leave it with these y squareds. How can I get some equation? I can see a minus sign there. That's good. So these minus bits can all come out. So really I've got y squared plus 2y plus 1. Okay, with a minus on the front. This bit, as I said, is already pretty much sorted. So we can deal with that now. So 6x squared over 3. Yeah, big tick. That's that bit sorted. Notice that y squared minus 2y, sorry, y squared plus 2y plus 1 is y plus 1 all squared. So I could factorize that bit to get y plus 1, or even better, complete the square and you would have noticed the minus 1 works fine. Okay. What does that mean then? Well, it means I'm almost there. If I could just write this as something squared, which is where the square root of 6 squared, you'll be surprised how many people just naturally put 6 down in front of it. But you don't, because you want this function squared gets you 6x squared. And there we go. I'm pretty much finished now. I can say that this transforms to that. What's the 2 transformation? If x goes to root 6x, that looks like a stretch to me. By scale factor 1 over root 6. It's the opposite way around, of course. And the y goes to y plus 1. So therefore that's a translation by 0, 1. So there's a sequence of transformations that maps that curve onto that curve. Always be wary in case the examiner tricks you out as well and wants you to work backwards the other way around. Okay? Right. Those transformations can be done in either order. It doesn't matter which order you do them. The translation and stretch isn't going to make any difference in that case because they are acting on opposite parts. So it doesn't make any difference. Always be wary and always think about checking. Okay, so you've got some exercises to do, some questions to do on exercise 3C on page 55. Make sure you have got plenty of those with the composite functions. Okay.